Nowadays, big prime numbers are used a lot in cryptography. These numbers are used to create big semi-primes called keys. But when I said big primes, you might wonder, how big exactly? Well, the primes of which these keys consist of aren't normal primes like 2 or 61, or even behemoths like this. In reality, the keys look like this, and the primes that make them up are on the scale of 10 to the 600th power. Or in other words, really huge. Like really. When I first saw these big prime numbers, I thought to myself, that seems a bit extreme. Wait a minute, how on earth could anyone verify that? These primes are like over 600 digits long. If they weren't primes, but instead had two factors of the same length, they would both be 300 digits long. And you may say, 300 digits? That doesn't sound like much. But think about it in this way. The universe is 4 quadrillion seconds old. That's only at the scale of 10 to the 18th, or in other words, 18 digits. And those potential factors would be on another scale. In practice, the point of keys is that they can't be factored in any sane amount of time. But that doesn't stop us from the more interesting question. How are big numbers factored? First, let's take a look at how a simple algorithm would fare against these numbers. Trial division is a simple algorithm that's probably the easiest to come up with. Let's see how it works in practice. For example, factoring 5063, we would start by testing whether it's divisible by the smallest prime, 2. In this case, it turns out it isn't. Then we would move on to the next prime, 3. But it turns out 5063 isn't divisible by 3 either. In the case of 5063, we would continue to check primes until we'd find that it's divisible by 61. From that, we would then get the factorization 5063 is 61 times 83. But what if we didn't find any factors? When should we stop? Well, one of the factors of any number must be less than the number's square root. Thus, we can stop at the square root. One thing to note is that in practice, we might check the divisibility of every number and not only the primes, since it's a lot easier to do so. Now, if we started checking factors for some big number 100 digits long at the beginning of the universe with a rate of about quintillion numbers a second, you'd still have to check about billion times more digits until you'd found out these potential factors. That's great if you're some sort of eternal being, since you've now got the answer, but to us mere mortals, time is a problem. The amount of possible factors grows about the same rate as the square root of the number if we aren't using any other techniques, and with that we would have to say goodbye to ever factoring these giant numbers. That brings us to the topic of the video, Quadratic Sieve. It's the second best factorization method currently known. The best method, general number sieve, is far more complex and out of the scope of this video, but Quadratic Sieve doesn't fall far behind, and it's still the best algorithm for factoring numbers less than 100 digits. We hope to give you an in-depth understanding of this algorithm so that in the end of this video you could, for example, program your own implementation of the Quadratic Sieve. When building up to the superior factorization algorithms, we have to look at Fermat's factorization. Have you ever tried factoring even integers and didn't find any factors? No? You'll of course spot the obvious factor, namely 2. Factoring 2 and its powers is luckily just as easy for a computer. Thus, every time we factor a number, we can first factor out all the powers of 2 and then take care of the rest of the number. After taking care of all the powers of 2, we are either done or what we have left is an odd number. Here, from this point onwards, we'll call the number to be factored n. The factors of an odd number are odd, and thus, if we draw them on a number line, we can see they have a middle point which is also an integer. This means that the factors can be written as middle point m plus a distance d and middle point m minus the same distance d. Some of you might have noticed that this actually is a difference of two squares. We can even get rid of the minus sign by a little rearrangement. This equation tells us that if we find a square number, we can add to our number to be factored and end up with another square. We have found a factorization for a number. Lastly, we might want to rename our two new numbers as a and b because we are going to see them a lot. Now if we find these a and b, then a plus b and a minus b are going to be our factors. For example, factoring 5063, we start by adding squares. If we add 1 squared, the resulting number 5064 isn't a square. If we add 2 squared, we again fail to produce another square. And the same holds for 3 squared. After trying a few numbers, we find that 5063 plus 11 squared is 72 squared. Now rearranging a little, we get a difference of squares, which in turn gives us a factorization of the original number. Let's take a closer look at Fermat's factorization. What happens if we tried factoring some multiple k times n instead of n itself? Well, the factorization would give us two factors, a plus b and a minus b. The real factors of n, n1 and n2, would be distributed in some way between these two numbers. Here are the ways they could end up splitting up between the two. The first factor could be k times n1 and the second n2, or the first could be k times n2 and the second n1. Or the first factor could be k and the second n1 times n2, or the factors could be reversed, for example n2 and k times n1. When we now take the greatest common divisor of these numbers compared to our number to be factored, we can see that in 2 of the 3 cases the factors are split between a plus b and a minus b. In the leftover case, we sadly won't get an interesting factorization of n, instead getting a trivial factorization n times 1. If we accept the chance of failure, we could write our original equation with an additional coefficient k. This might seem like a really weird move until you notice that we can now express the equation as a congruence relation. This gives us just a bit more flexibility that allows us to construct the quadratic number sieve. Before we begin, we need to pick a number b. Alongside this number, we'll introduce a new term, b-smooth. A number is said to be b-smooth if all of its factors are less or equal to b. For example, let's set b to 13. Now all the numbers that have factors bigger than 13 are not 13 smooth. For example, look at the number 20. We can factor it to 5 times 2 times 2. All of these factors are less than 13, so this number is said to be 13 smooth. The number 34, however, is not 13 smooth because it factors to 17 times 2. Here, 17 is bigger than 13, so the number doesn't fit our criteria. Remember that we can choose b arbitrarily and the speed of the algorithm will depend on the value of b. We'll come back to choosing b at the end of this video. For now, let's stick to 13 and get on to the algorithm. The algorithm consists of 2 parts. In the first part, which is really the core of the algorithm, we find b-smooth numbers and store them for later use. The latter is responsible for finding solutions to a matrix we construct of these numbers. For now, we don't need to worry about the second part, since we'll first look into finding b-smooth numbers and come back to the matrix representation later. The algorithm starts by finding some amount of numbers which square modulo n is b-smooth. We'll come back to why we're doing this a bit later, but for now that can be a bit too much to comprehend. So let's look at an example. Let's say our ultimate goal is to factor the number 1817. In the real world, we would use the quadratic sieve to factor much bigger numbers, but let's take things slowly for now. The first thing the algorithm does is it takes a guess. Let's say 43. We square this number and take the modulo. We use 1817, the number we are trying to factor, as the modulus. We want the resulting number, in this case 32, to be b-smooth, so we factor it and get the following result. As all these factors are less than 13, it turns out that 3 indeed produces a b-smooth number. We need to find several numbers like this so we can increment our guess and repeat until we are happy with the amount of data we have. This procedure is mostly trial and error, and apart from some optimizations, there is little we can do to get the results faster. Hold on, did you catch that? We factored 33 in a factoring algorithm. How on earth did we do that? Isn't the ability to factor the very thing we are building here? Well, the Quadratic Sieve is a very good algorithm for factoring really large numbers that are the product of only a few primes. In this case, however, as a part of the process of factoring, we want to factor a small number that, in contrast to the actual number, is really fast to do with even basic methods. In addition, Quadratic Sieve only finds one factor for a number, and in the case of these smaller numbers, we want to find all the factors. We'll use sieving to compute that. To sieve a number, for example 4840, we start by checking possible factors one by one. On the top here, we have all our primes up to b. Remember, we set b to 13, so if all the factors of our number 4840 are currently somewhere on that line, this number is b-smooth. We start by checking whether or not our number is divisible by 2, the first prime in our list. It is, so we divide the number by 2 and take note of that we have factored a2 out of this number. Alright, let's continue. Can we divide it again? Yes. We can repeat this checking and dividing, always remembering how many 2's we have extracted out of our number. When we can't divide it anymore, we move on to the next value. A number doesn't divide 3, so we move on. 5 on the other hand is a divisor of our new number, which means we can extract it out. Dividing by 7 doesn't give us an integer, so we move on. And finally, we can extract out 11, twice actually. At this point, our original number has reduced all the way down to 1. There are no more factors, so we have reached our goal. 4840 is indeed a 13 smooth number. Notice how if we had checked all the way up to 13 without our number reaching 1, it would mean that the number contained some bigger factor. This means that if we reach 1 in our algorithm, we can say that the number is b-smooth, and if we don't, the number is not. Anyway, after that little tangent and some computing, we have found the following results and stored the factored forms of the right side. Now you might start seeing why we are squaring and taking the modulo. Remember that our original goal is to find two numbers a and b such that a squared is equivalent to b squared modulo n. If we can find such numbers, we can use the work of Fermat and Raychick to solve our problem. Luckily, the numbers we have computed already closely resemble what we want. If we could somehow get the right side to also be a square, we would be golden. And here comes the ingenious part Raychick originally came up with. If we multiply some of these equations together, meaning we multiply the numbers on the left together and the numbers on the right together, we could get an equation with squares on both sides. Because all the numbers on the left side are already square, we can multiply any of them together and it still gives us a square. That is because we can extract the exponent outside the brackets. Keeping this in mind, we have effectively transformed our problem of finding factors to a number into finding some combination of these equations that gives us a perfect square. Let's focus only on the left side for a moment. This task might seem daunting. After all, it doesn't seem like we have gotten any closer to the goal, but if we represent these numbers in a factored form, we can get somewhere. Notice how multiplying these effectively means adding up their exponents. If we can figure out a way to get all the exponents of these primes even, we can extract the 2 outside, and would you look at that, we have just created a perfect square. So multiplying some combination of these numbers together, we hope to be able to get every exponent even, which results in a perfect square. Make sure you understand this idea before moving on. Now, let's also include the hidden 0th exponents. Anything to the power 0 is 1, so these terms are meaningless, but they'll show the algorithm nicely. The way we guarantee an exponent is even is working with modulo 2. If a number is even, it will be equivalent to 0 modulo 2, and if a number is odd, it will be equivalent to 1. To make things easier, let's introduce a new variable. We can use x with some index to answer the question, do we want to include the number with the index in our product? With this new boolean, we can write our exponents a bit differently. Let's take all the 2's exponents and form the following equation. This represents what our exponent will be depending on what numbers we want to include. If we want to include some number, for example the first one, we can set x1 to 1. If we do not wish to do so, we can set it to 0, effectively neglecting the term. Our goal is to get this expression even, which can be better understood if we take modulo 2. Now we can simplify a little bit. The 4 is even, so we can turn it into 0. This should make sense since adding any amount of these terms doesn't change our number's parity. Correspondingly, we can reduce the 5 to a 1 and do the same simplification for the rest. We want to find some values for the x's that satisfy this equation. Of course, the equation as it is rather simple. We could set x2 to equal to 1 and all the others to 0, which means we include the second number in our multiplication and ignore everything else. We, however, want all the exponents to be even, so let's take the others into account. This seems like a linear system of equations, doesn't it? And how do we solve a linear system of equations? With a matrix, of course. In math notation, it looks like this. The rows represent prime numbers, while the columns represent numbers we have found. This one is practically answering the question, does the second number have a factor of 7 and is the amount of 7's odd? We won't go into solving the matrix here, but if you are interested and have 10 minutes to spend, this video has a great example to get you started. The important thing to note is that we are solving this matrix in modulo 2, which means that 1 plus 1 is 0. This stems from the fact that two odd numbers added together make an even number. One possible answer to this equation, which we'll be showing here, looks like this. This tells us that we need to include the first and the third term and ignore the rest. So we can get our 4 numbers back and only focus on the 2 that we care about, the first and the third. Now we can multiply these numbers in the same modulo equation without breaking math. Since we did all that work with the matrix, we can now guarantee that the right side is a perfect square. With some rearranging, we can extract the square out of both sides. When all the dust settles, we have found ourselves 2 numbers, which can be applied to the formula that you are all by now hopefully familiar with. We are at the home stretch, I promise. Remember how we talked about that if we have these 2 numbers a and b, we can solve our problem? Well, now we have those. We just need to take the greatest common divisor discussed before and get our result. We can substitute a and b to the formula, and there we have it, 23. We can get the other factors by just dividing n with this factor, and we get 79. Now it is possible that we could have gotten 1 or n out of the greatest common divisor. In this case, we got the answer straight away, but especially when we are dealing with larger numbers, it is possible that we get one of the 2 trivial solutions. If that happens, we calculate another solution to the matrix and try again. That was a lot of theory, so it will be useful to draw out the outline of what just happened. First, we needed to calculate 3 variables. B limits how big our numbers can get. Then we picked some amount of data we wanted to gather. In the example, we gathered 4 numbers. Lastly, we took a first guess. Next, we took guesses of numbers and checked whether their square modulo n is b smooth. If it was, we appended the number to our data, otherwise we just moved on, always incrementing our guess at the end. When we decided we had enough factorizations, we moved on to building a matrix from our data. Each column in the matrix represented one number in its factored form. each individual number showing whether the exponent for that prime is odd. A lot of effort was put into grasping the idea behind it, but the actual computation, as you can see here, is quite straightforward. Afterwards, we solved for one solution and we tried if it works. This was done by taking the greatest common divisor. We can repeat this until we find a valid solution. Finally, if we run out of answers to our matrix, we can always increase the data required and resume the first step of finding more data. We, however, have 3 different variables to choose every time we factor anything. We need to choose b and where we start the guesses, as well as how many b-smooth value we want to compute. Let's start with the quickest one first. How do we choose b? There actually exists a formula for calculating the optimal value for b. This one right here. It might look scary, but it's a one-time calculation before we begin our program, and it's really just a bunch of operations surrounding n. The output of the formula grows gradually as n gets larger, but computation time not as much. Alright, that one done. Next, where do we start guessing our numbers? I think it should be quite intuitive that working with smaller numbers is quicker than working with larger numbers. In this case, however, especially so. The probability of a number being b-smooth is greater for smaller numbers, since larger numbers can have very large primes in them. We can recall the formula for calculating a possible b-smooth value for a guess. In practice, this means we want this resulting number to be as small as possible. The motivation for taking a square root of n and sealing it should make intuitive sense. The guess is squared, which will effectively negate the square root, and sealing the result of the square root gives us a number that when squared is just a touch bigger than n. Because our new number is a tiny amount greater than n, when we take the modulo n of it, we end up with the difference, which hopefully is rather tiny. Choosing the amount of b-smooth numbers is also somewhat straightforward. Without going too much into the details, more data means more possible solutions for our matrix. To go along with this, if our matrix is a square, we have guaranteed at least one answer. Since it is possible that a solution gives us an invalid result, we should have multiple solutions for the matrix. In practice, we usually wait for 4 or 5 more numbers than the rows in our matrix. In other words, the amount of numbers is the amount of primes up to b plus 5. This gives us plenty of opportunities to get the correct number. The last thing we can do to this algorithm is to optimize it. Now, I could go on forever about optimizations to this algorithm, but let's add one more block to our tower. I'll show you one more optimization cause it's so major and it accelerates our algorithm a whole bunch. We'll use something called Euler's criteria to filter out some primes from our prime list. You may have noticed that some rows in the matrix in our example were all zeros. There is a good reason for that. As it turns out, it is impossible for these primes to occur in our data. In other words, no matter how much more data we could have gathered, we wouldn't have seen any number with a 3, 5 or 11 as a prime. By calculating what numbers can't show up, we can eliminate them beforehand. This way we can save up space and speed. At the start of our program, we can go through every prime up to b and check for Euler's criteria. Euler's criteria shows us if an integer, in our case n, is a quadratic residue modulo a prime. That is a bit much, and it's fine if we don't fully understand what it means. The gist of it is this. We can do this simple calculation for each prime and look at the result. If it outputs 1, the prime can occur and we should add it to our prime list. Otherwise, the modulo will give -1, which means we can discard the value because we won't be seeing it in our data. This is huge, since in the sieving process we must only check for values that pass this test. After all, there isn't a point in checking 5, for example, if we can't find it as a prime. Additionally, we can fully remove these rows from the matrix, saving us space and speed. Notice, however, how the 7 row has all zeros, yet we still don't remove it. 7 actually passes the test, which means it is possible to get 7 as a prime. It just didn't happen to show up in these numbers. With this matrix, we have halved the height of it, so we can probably imagine how when working with much bigger numbers, this is a huge time save. And that is it. This hopefully has given you an in-depth understanding of the algorithm, so that if you want it, you could go and implement it by yourself. With these optimizations, the program should be able to crack a number around 30 digits long, but with more optimized versions, it could be doubled. The only thing left unexplained is solving the matrix, but that isn't really part of the core of this algorithm, is it? The reason behind creating this video is the lack of good resources on this algorithm. We were only able to find one good article on the topic. Regardless, we hope you have learned something, or at the very least, had a good time.